Welcome, everybody. Good afternoon. Welcome to the talk measuring the performance of CPython by Michael Droettboom from Microsoft. The stage is yours.
So much. All right, so I'm going to be talking today about how we measure the performance of CPython. And CPython, for those who don't know, that's the sort of most popular implementation of Python. So most of the time when people say their program's running on Python, what they're really doing is running it on CPython, though there's alternatives, obviously. So you might have come to this room to answer the question, how do I make my Python code faster? And usually in that situation, you have a program and about 10% of its code takes up 90% of the runtime, and so you figure out where that function is, and you might add some decorators, and it magically goes faster. Well, this is not that talk. If that's what you came for, no offense if you want to leave now. You might have come here thinking, how do I make all Python code faster? Well, if you're on a language team like mine, you might know that you translate the Python into bytecodes, and then you have a runtime specializer, and that might go to another kind of IR and an optimizer and machine code. Well, sorry to say, this is also not that talk. There's actually a good talk by Brant tomorrow that's much more in that space. You might have come to answer the question, how do I know that I'm making all Python code faster? Well, this is that talk. So obviously, at a fundamental level, what you have to do is time it. You have to have a stopwatch. You just want to be timing code. But there's this whole level of complexity below that that you need to sort of grapple with when you're trying to answer that question. One is, what should we measure? How do we build a better stopwatch? And lastly, how do we scale up that stopwatch so we can share it with a bunch of people? So before I get into all of that, a quick overview of me. I am the manager of the Microsoft CPython performance engineering team, and which is part of the larger, faster CPython team, which includes people outside of Microsoft, at Meta, and in academia. And this is the group of people that work to make Python 3.11 between 20 and 60% faster, depending on what you're doing. And is also building the groundwork to make future versions of CPython faster. And some of these people are also CPython core developers, and so we all kind of work in the rules of that community and its structures for committing code and reviewing it and such. And so in my role as a manager, my biggest concern is, are we working on the right things? Are we working on the things that will have the most impact towards Python performance? And so that's why I got very interested in this topic of benchmarking and what I'm going to talk about today. And then also, because we are a community serving project within Microsoft, we also want to be able to help people outside of our team who are also answering and working on the same problems. All right, so part one is measurement targets. So let's start with the most naive approach possible, which is, why don't we just, this is something I was used to say, why don't we just measure the time spent in all Python programs in the world, right? So you could imagine the analogy of a marathon. You have all these runners. You could just take all of their run times, and then, I don't know, as they cross the finish line, compute a mean of all of them, right? And this is actually not that crazy of an idea in software engineering. For example, Firefox collects the time that every page takes to load. In everybody that opts into telemetry in Firefox, that data gets collected and then analyzed in the back end. And for projects like that, it works fairly well. But when you look at programming languages, it's a lot more. It's a much bigger problem. And the only other language I'm aware of that even came close to this space was Go, where they decided to add telemetry to, not to actually Go programs that are compiled, but to their infrastructure, like how long it takes the Go programs to compile and link and things like that. And even that had a lot of pushback. But they also didn't really even aim to solve the problem of, is Go getting faster with that telemetry? It's really just, is the developer experience getting better? So there isn't really any precedent for doing this kind of thing with a programming language. And the main reason is just that there's too many uncontrolled variables. Everybody in this room is doing different things with Python, and their code is changing all the time, and there's sort of no like fixed reference point that we could use if we just started doing that. And you see this even going back to my analogy of marathon runners. You might have this assumption that over time, marathon runners are getting faster just because training is better and people know what they're doing and the science of it, especially at the high end, is getting better. But in fact, what it is, there's this totally unrelated variable, which is the temperature on the day of the marathon has the most impact on how long it takes people to run the race. So it really doesn't have anything to do with the runners, which is what you would think you'd be measuring. So the answer to all of this and the controlled variable problem is benchmarking. Where basically you're creating a robot runner that will do the exact same thing every single time, and then if you change one thing, you know that you're actually measuring the effect of that one thing and not all this other uncontrolled stuff. And in the Python world, our benchmarks are in something called the pyperformance suite, which is about a collection of a little over 100 benchmarks. And this is the list of all of them, and there's this really kind of like cool history and family tree to them. They're sort of like folk wisdom that has been passed down over many, many decades. So some of the benchmarks in there really are 30, 40 years old, and they started in some other programming language and got converted to Python at one point. But I would say, you know, as a way of thanking the previous work on this stuff, I would really mostly want to thank all these other projects that have aimed to make faster Pythons over the years, like Unladen Swallow and PyPy and Piston, and then the faster CPython team, have sort of contributed to this big group of benchmarks over time because they care about the problem. And what gets really interesting is not all benchmarks are created equal, and this textbook from the 90s has actually, I think, a very useful chapter for looking at benchmarks and for putting them into different categories and deciding what they're useful for. So they basically have these categories. They have toy benchmarks, which are very simple, usually less than 100 lines of code, but often are doing something that, while cool, is not representative of the kind of things that people do most of the time. And then another category is real applications. So you're taking some code that actually does run in production that maybe is like behind Instagram or some big massive scale application like that, and you're running all of that or some of that in the benchmark suite. Subclasses of this would be like modified applications where you change it slightly to make it better as a benchmark, or an application kernel, meaning you're just taking one subsystem of that application and benchmarking that specifically. And then there's another category, important category of benchmarks that's not actually in this textbook called micro benchmarks, where what you're measuring is one very narrow feature of the language. So it might be something like list comprehensions and just like how fast are those getting. And so to give you some examples from our suite and how they fit into those categories, like a good toy benchmark in there is the N Queens benchmark that, given a chessboard of a particular size, figures out how to put the queens on it so that no one can attack another one. Like, it's cool, but most of the time, most of the Python code in the world is not playing chess, probably. There's another one called Richards, where Martin Richards in, I think 1981, wrote a toy network protocol that's never been used in production as far as I know. But it's just like this little toy that does a network protocol and sends things over a virtual wire. And then this got picked up and started in C and then was converted to Java and eventually Python. And it has this whole big, long, convoluted story, some of which is in the comments. So that's the kind of thing you get. And if you look at other language communities, toy benchmarks have been kind of controversial because they're very easy to game. So like the web community at one point had a benchmark suite that was just full of toy benchmarks. And the browsers all got much better at doing those toy benchmarks, but it wasn't really having a huge impact on real-world websites. And so they got, there has been this movement in that community to move away from those into newer benchmark suites that are much more representative. They sort of start with what like Facebook does and then work back from there to create a benchmark that could run everywhere. And so that's kind of what the web world has done. But a contrary view of toy benchmarks that I think is also important is like, if it's only 100 lines, a developer has the time and the ability to look at those 100 lines and really understand what they're doing in a way that an application that might have 1,000 dependencies with all of these layered calls one into another, it's much harder to reason about. And so I know on our team we found it very useful to have these toy benchmarks because we can actually reason about them, and when we see something that's weird or unexplained, it's much more efficient to figure out what's going on. So I would say like both of those things are true at the same time. That's how I view toy benchmarks. Okay, then on to micro benchmarks. There's a comprehensions benchmark in the suite that just has list comprehension and a dict comprehension, and then a list comprehension inside of a dict comprehension, and on and on and on. There's a garbage collector benchmark that just deliberately creates objects with reference cycles and then measures how long it takes to collect them. So obviously that's measuring that garbage collection subsystem of CPython, but not broadly how Python code generally behaves. Because usually if you're going to make all these objects, you're actually going to do something with them, and this benchmark doesn't do that. An example of an application benchmark in the suite is Django CMS. So this is a full-fledged web application that runs a CMS, and there's a benchmark that has sort of a example site in that, and it measures how long it takes to serve that web page. So this has all the library dependencies and what have you that you would expect of a real application. It's measuring all of that. An example of a modified application benchmark would be something like the pylint one, where it loads a large Python file into memory and then lints it, but we only measure the time it takes to lint it because we don't want to have the I/O, the time it takes to read it off of disk, impact the benchmark. And then a kernel benchmark would be something like docutils. This just takes a really large restructured text file and converts it to HTML, which is, most people don't use docutils directly. Usually they use it as part of Sphinx or something, or is serving a documentation website. But this is just measuring kind of that important bottleneck within it. And another kernel benchmark we have is the SQL Alchemy benchmark, which brings up, I think, another important problem with application benchmarks, which is SQL Alchemy depends on the Greenlit library. And Greenlit is one of these libraries that reaches very deeply into the CPython internals. So as we develop CPython and make changes to things that are not really meant to be public, Greenlit breaks every time. And you can see this, there's this very long pull request that's been going on for months between a core Python developer and the Greenlit developers to get it working on 3.13. And it's all very collaborative and great, but it just takes a long time, and it takes expertise on both sides of it. And so often what happens is these application benchmarks break fairly frequently for us because we are, by our very nature, measuring the bleeding edge of CPython, where a lot of code doesn't work yet. It's pre-releases of CPython and all things like that. So to summarize, I think all of these benchmarks are really useful, which is why we keep them all around, but they're just useful in different ways. So application benchmarks are great for answering how much is Python getting faster, but the toy benchmarks are better at answering why they're getting faster. And so if you take the benchmarks in the suite and you organize them by these categories, so application, toy, and micro benchmarks, you see that about half of our benchmarks are micro benchmarks, which is probably not great for measuring the overall increase in performance. But if you actually look at the changes, when you take the mean of everything, it's actually pretty close to what you get for the application benchmarks. So when you have kind of enough benchmarks, it all kind of blurs into something that's pretty close to the same measurement. But I think it is important to have the ability to look at the data this way as you're working to kind of make sure you're looking and measuring the right things. Another thing we do with the benchmarks is we can measure where each of the benchmarks spend their time. So on a regular basis, we run all the benchmarks inside of the Linux perf tool, which is a sampling profiler that works at the C level. So it's telling us which C functions within the CPython interpreter it's spending its time. And then we've kind of manually classified all of the C functions in the interpreter into these high-level categories. So the big one there you see is interpreter. So this is the big loop that goes over all the bytecodes and actually makes your Python code run. But then the next category there is memory. This is anytime an object is allocated or deallocated, we include it in that bucket. The GC is anytime it's collecting cyclical garbage, so references that wouldn't otherwise free immediately. And the next category there is library. So this is C extension code. So for example, the JSON parser in CPython is actually written in C. And so the time that you spend in the JSON parser would show up in that category. And then they get a lot smaller beyond that, but I think it's also interesting to note like the kernel category there at about 4% and libc at about 3% is actually code outside of CPython. So that's either the Linux kernel or the standard C library, and that's kind of code we don't control. And obviously we can try to call out to it less, but that's also included in the numbers, obviously. And you can also do this same analysis on a benchmark by benchmark basis. And this gets pretty interesting, and it goes back to some of the things I was talking about earlier. So the list comprehensions micro benchmark spends a lot of time in the interpreter. You would sort of expect that. Whereas Django CMS, which is an application benchmark, is a lot more diffuse. It kind of spends its time all over the CPython runtime. The GC collect benchmark obviously spends most of its time in the GC. That's not surprising. And the JSON benchmark has a lot of library code because, like I said, that's written in C. And so having this understanding of how each of the benchmarks behave actually helps us as a team kind of understand when we see certain benchmarks moving in certain ways, kind of why that might be based on what we're changing. So you can also, again, group the benchmarks based on where they spend most of their time. So what I've done here is for each benchmark, the number one category that it's in, we put that here. So 54 of our benchmarks spend most of their time in the interpreter, and then we have a bunch of other benchmarks spend most of their time elsewhere. It's really interesting. Some of the benchmarks spend most of their time in the Linux kernel, so they're really not CPython benchmarks at all. They're Linux benchmarks. And then if you look at the speedups based on this, this is actually not surprising at all. Most of our effort over the past few years has been working on the interpreter itself and trying to make that faster. And so only the benchmarks that spend most of the time in their interpreter really got faster over that time. Benchmarks that don't spend most of their time in the interpreter, we haven't really seen any improvement. And that's fine. I mean, it confirms what we've been doing. It also shows, places for future improvement outside of the interpreter. And then the other thing we generate on the regular basis is these distribution plots. So for each benchmark, we can kind of see how much faster they're getting and the distribution, because it is sampling and there is noise in the data. And this is also just sort of helpful in getting a better understanding of how each benchmark's behaving. I'm going to show this slide again later with some more context too. All right, so my call to action after this part is if you care about a particular workload going faster, please donate some benchmarks. So if there are certain things that your applications are doing that are important, that are not really being represented in our benchmark suite, the best way for us to help you make your code faster is to have a benchmark in that benchmark suite. So there's two ways you can do this. You can make a PR to pyperformance, and we can review it and merge it. Or you can keep the benchmarks living in your own repository, and then all we have to do is basically point to it. As long as it's open source and we can download all the requirements, that's fine. All right, so on to part two, building a better stopwatch. I'll step back a bit here at the beginning. benchmarks are really most interesting when you're comparing them to something else. So you benchmark A against B, right? And there's all kinds of different ways that people are interested in doing this. This kind of like old thing when everyone was like, my language is better than your language, was to do these language comparisons. So you might compare Python against Java against Go and C. And I think the world has understood this is not a terribly useful exercise because you have to actually rewrite all the benchmarks in a different language, and then you argue about whether it's idiomatic to Python or not, and all of that. So that's one thing that people used to do a lot. Another thing you can do is compare different implementations of the same language. So you might be comparing CPython against PyPy and Cinder and Pigeon and all these sort of alternative implementations of Python. Speed.python.org is sort of mostly focused on that comparison, though just by kind of historical accident. The one world where I spend most of my time on this team is this development comparison, where you have CPython main upstream, and you have a pull request against it where you're making a change, and you want to know, did my change help or hurt, right? And so you're just comparing, pull requests against main. And then this last one is maybe surprising for folks like myself who don't have a strong background in statistics, where you're comparing the same thing against itself. And the reason this is useful is it can help you figure out where the noise is in your system, or how much noise you have. Because you really take exactly the same thing and you run the exact same experiment on it 2 times, and then you see how much they agree, right? And so we know from the AA testing that we've done with pyperformance on CPython that the noise we get is around plus or minus 1%. So that is just noise in the system from various sources that I'm going to get into. And the problem you have is most performance improvements that we've seen, even when we were working on 3.11 and making it go faster, most of the improvements are not these like big aha moments. They're these small, less than 1% improvements that you stack on top of each other and eventually get somewhere. So it's really important that at every step of the way, you're reducing the noise as much as possible. You can use additional signals that are not just timing to kind of tie break when things get murky. And then there's also a few statistical methods I'll talk about that help eliminate some of this noise. So what are some of the sources of this noise? A big one is just kind of other things happening on the system. So obviously all our operating systems these days are multitasking operating systems, and they run other processes, and those have the possibility of interrupting your benchmark and introducing noise. So there's 2 techniques that are used there that reduce this. You can isolate certain cores so that they are basically not going to be used by the system and by the kernel. And then you can, when you run a process, you can say, please use this core and only this core, which is CPU pinning. And when you combine those together, you can kind of dedicate one of your cores just to the benchmarking, which prevents other processes in the kernel from interrupting it. Obviously, a lot of stuff happens on virtual machines these days, and that is like this problem only amplified 10 times. And so we basically do all of our benchmarking on bare metal machines just to avoid any of that noise of virtual machines, where you have both the virtualization layer and other virtual machines on the same host kind of getting in the way and mucking with your results. Another thing that happens on all hardware these days is thermal management, right? So CPUs don't run at a fixed speed. They generally try to use as little energy as possible most of the time, and then when you do a bunch of work, they'll increase the speed, but then what happens is it gets really hot and you get close to like the CPU burning, so then it has to slow it back down again. And so this graph kind of shows that a little bit, like the left side, the machine is kind of idle, and then on the right side, we start running benchmarks, and you can see that the temperature of the second chart goes up, but then it has to like throttle the CPU. So you get all this like speed up and down that introduces noise. Another source of noise is memory layout. So every time you run CPython, the objects will have a unique memory layout. There's lots of sources of this, but like, in one run, your 2 objects might be really close together, so jumping that pointer is fast, or they might get really far apart and it gets slower. And there's not too much you can do about this. And this is actually a security feature, right? They don't want hackers to be able to predict where certain objects will be, so they'll randomize it at runtime, and it's just a fact of life and something that's always going to be there. And then also each build of CPython is going to be different. Because we do profile-guided optimization, where we let the compiler figure out which are the hot parts of the code and which are the cold parts and move them around, the compiler is free to reorganize the code every single time we build Python, and it's a little non-deterministic because it's based on running benchmarks, essentially. Lastly, the source of noise is like in the benchmarks themselves. And so short running benchmarks, if they take like under a nanosecond, are really, really hard to measure because that's just so fast, and the overhead of the measurement is so large compared to what the benchmark is actually doing. And so the common solution to that is if you have a really short running benchmark, you run it a bunch of times. And actually, our infrastructure handles that automatically. It will run the benchmark a few times and kind of make an estimation, and then it will figure out how many times it should run it to get a stable result. And related to that is this concept of warm-up, where often the first few times you run a benchmark, it might be loading things from slower memory or even from disk. And so those first few times are a lot slower, but then after you run it enough times, it kind of flattens out. And so our infrastructure also automatically will kind of determine when that curve starts to flatten out and then only use the flat part of the curve for the measurement. Another thing you see is, and you can probably see by looking at this graph, one of these kids is not like the other. Most of them fit this kind of nice normal distribution around the mean, which is what you expect. It sort of has like how it behaves and some noise around it. But the pilot one there you see has this weird bimodal distribution, which suggests to me there's something wrong in that benchmark and we need to go in there and figure out. It's probably doing I/O where we think it isn't, so the first few runs are slow and then it gets faster, but I'm not sure. And so all of these things that I just talked about are encapsulated in pyperf. So I was talking about pyperformance earlier. That's the suite of benchmarks. Pyperf is a library that is designed to solve all of these benchmark measurement problems and encapsulates them in code. So all of these little details I talked about kind of get taken care of automatically. Oh, yeah, that's... okay, and so then the last way we deal with some of this noise is statistics. The sort of classic way to take a bunch of benchmarks and then turn that into one number has been the geometric mean. It's very straightforward, but it does sort of assume that most benchmarks are created equal and you want them equally weighted, which isn't always the right thing. Like your micro benchmark that does really well on something maybe shouldn't have a great influence on the big number you're using to say how fast CPython is. And so then the other thing that people talk about is using a weighted mean where you just multiply each of your benchmarks by a certain weight. And ideally you select those weights based on what goes into a typical workload. So if you know that 20% of Python code has a list comprehension or whatever that might be, you would weight that benchmark a certain way. But it's a little bit of a cyclical problem, because if you knew what went into a really good workload, well, it's actually a lot easier to just write a really good workload benchmark. So I haven't put a lot of effort into this, and I'm not sure it helps versus just adding more good workload benchmarks. But one thing that we do is this technique called hierarchical performance testing, which there's a paper about this that when it shipped in the spec benchmarking suite for sort of benchmarking hardware, where they only include results in the overall average when they're more likely to be different from the null hypothesis. So it's good at kind of ruling out the benchmarks that don't tell you anything and only including the ones that clearly have changed or made a difference. And I'm absolutely glossing over the math there because I don't have time and don't want to get, I'm not even really qualified to go into it, but there is the paper if you're interested in it, and it's pretty good, and there's code and all that stuff. All right, so lastly, we have the benchmarks. We know how to measure them. we don't want everybody to have to do all this themselves because it's very time consuming. So I built a tool that's kind of in this space of continuous benchmarking. And obviously continuous benchmarking is analogous to continuous integration. So if you've used GitHub Actions to run your build your library and then run your test suite, that's continuous integration. Continuous benchmarking is doing the same kind of thing, but for benchmarking. And here we have a set of bare metal machines that everybody uses. We use the same ones every time just to eliminate any variables of, slight differences in hardware or OS configuration or things like that. And it's all sort of built and orchestrated on top of GitHub Actions and their self-hosted runner concept. Anyway, because why rebuild? Why rebuild the wheel of doing this work in a distributed way? And what this does, this is just a screenshot from our GitHub Actions repository for this, where you can say, for my fork of CPython and this branch that I'm proposing as a pull request, run it on these machines and report back. And it produces this whole table of results. The URL is there. It's publicly available for anyone to see our results. And once you create enough of these results, you can create these pretty graphs of how it's changed over time. So this one is actually a little bit interesting, and this sort of shows the development of Python 3.11, where at least on Linux, it got quite a bit faster over time, but then I think what happened was, this is just my own personal hypothesis, I think what happened was there were a few bugs in there, and we fixed them that made it just slightly slower right before we released. But anyway, you can kind of see these things. And if anyone is concerned about Microsoft taking over Python and us devoting all these resources, you can see that the one platform that actually got slower in 3.11 is Win32. So we're not just focusing on our own products. And that's just by accident. It was not. And so I think continuous benchmarking is really powerful, but it's still in this world where continuous integration was maybe 10, 15 years ago. Continuous integration is very mature. You can just go use GitHub Actions today and everybody does it. Continuous benchmarking requires just a little more administration. You have to own your own machines, or you have to rent bare metal hardware in a data center, and the prices on that are they don't even tell you the price. So I think that means expensive. And the last thing that's actually pretty frustrating for me personally is, because you're running on bare metal hardware, you can't just let anybody submit a PR, because it's a huge security risk for them getting access to your machine and having that persist and all of these things. And so we do have to have it kind of limited to our team. We do, if someone asks us nicely to run their PR on our infrastructure, we're happy to do it after we vet it and read the code. But that adds kind of an extra human step in the middle that would be nice to have a solution for. All right, so to sum up, a few things that I would like to see improve with all of this. The first one, I'm calling this meta performance optimization. The pyperformance suite itself is probably wasting a lot of time. It takes about an hour and 10 minutes to run on our hardware, which is not forever, but if you want results, you have to do an hour and 10 minutes on your change and then an hour and 10 minutes on main, and then compare them. And so it takes 2.5 hours to get your results. And if you're on a team of 6 people and you have, say, a release freeze the next day, you pretty quickly run into where you're waiting all day for your results. And so I think there's quite a few benchmarks in that suite that are doing more work than they have to. For example, they might be running longer than is really needed to measure what they do. So doing some work to kind of cut down on some of the longer running benchmarks while still retaining what they tell us would be super useful. With the continuous benchmarking that we have this pretty good data-driven decision-making loop where people come up with ideas, that becomes a pull request, they run it on the benchmarks, and then if it's faster, you merge it, if it's not, you don't, right? So we kind of have that process going. But I think the next step here is when you run the benchmarks and you realize it's not faster and you don't merge, that there's kind of enough information left over that comes back and generates new ideas for you so that you have something to try next or more information. And so we do have some things in that space already, but I would really like to see that loop kind of close and get tighter and faster. I think that could be very powerful. And then lastly, I mean, we all know, especially from the last talk and other talks here at the conference, that the future of Python is going to be more parallel than it is now. And all of these benchmarks that I've talked about are all single-threaded benchmarks. They're measuring the time on a single core, running straight through in CPython, no communication with other cores or any of that. And so as Python, either with subinterpreters or with the free threading change, starts to become more parallel, we should be measuring that as well. But we need some good benchmarks for that, and we need to understand what those workloads are like, and we need to, create them in a way that's realistic and will tell us new stuff. But right now, we don't really have any insight into that. We can tell you that when, you turn free threading on, we know that single-threaded performance changes, but that's not really the point of free threading, so it's not the best. All right, so that's my whole talk. Hopefully there is some time for questions. And once again, my call to action, please submit your benchmarks. Either look out for me or come to the pyperformance repo on GitHub and reach out to us there.
So for the meta performance optimization, do you spend a lot of time looking at like covariance matrices for the benchmarks to try and, like cluster, like are two benchmarks telling you like the same information or not?
I've done a little bit of that, but nothing that, I mainly did that as a way of finding benchmarks that just are not helpful at all. So that's related, but maybe a subset of what you're saying. I think that could be really interesting. If we could write one workload benchmark that just matched all the others, that would be great. But I guess I would worry that it might work. It might make sense now with CPython as it stands now, but over time it may no longer be covariant with all the others. So you still kind of have to keep doing it. You could run those less often. Totally. Yeah. It's a good idea.
Hi, really interesting talk. Appreciate your time. My company has a CI workflow that essentially right now is running, let's just say, multiple processes, multiple commands in sort of like a framework, a testing framework. And we're finding that the results we get are really nonsensical in terms of like any value whatsoever. Would you say that using benchmarks at like a unit testing level in terms of really isolating your concerns, say with like a module level or specific functionality, would you say that there is tools within PyPerf that would be useful for that, or recommend that as a workflow?
Well, PyPerf might help you reduce some of your noise. It sounds like what you're talking about is sort of like having a whole bunch of micro benchmarks that then would help like identify places that are regressing or something. Right. I do think that stuff is kind of useful, especially if what you're mostly concerned about is like changes causing major regressions, rather than, I think, our focus on just trying to get the needle going up. In a previous life, I worked on a tool called airspeed velocity that's much more focused on micro benchmarks and has sort of different sets of analyses around those, and can cluster them in a way that will show you kind of where changes are happening. So you might want to look at that too.
Okay, yeah. You said it's air.
It's called airspeed velocity.
Airspeed velocity.
It's a Monty Python reference.
Nice.
Yeah.
Okay, cool. I'll have to watch that. So. Sure.
Hey, so a lot of the issues that you have come from noise in the environment that you can't really remove from, so particularly the way the OS operates. Have you looked into any ways of getting rid of that, for example, by using simulation? Because you could abstract away those issues. And I'm also kind of curious to know, there's one way of doing it is with simulation. You could simulate your whole CPU or system architecture in some way, and normalize whatever the sources of noises are, just normalize them to some constant. The other thing that you could do is you could use tools like Mozilla's RR, which does deterministic replay, so you could completely eliminate the effects of, say, I/O when replaying something. And I believe Microsoft have something similar as well that's part of their debugging stuff. So yeah, curious to know if you've done anything like that and what your conclusions were.
Yeah, so I have played with some simulators. There's I'm blanking on the name of it, but there's a simulator that's used to like determine how big your cache levels should be, like how much L3 cache you should have, and this for a particular workload, and you can run it through. And I think Intel sponsors that project. I've played with that a bit. It didn't. It's very hard to get going. was one part of it, but also the data that it kind of gives is mostly around things like cache levels and not so much instruction and branch prediction and things like that. I mean, the other statistics you can get fairly easily are like instruction counts that are they're kind of a proxy for time, but not a very good one. But they're probably more deterministic at least. And there's tools like a cache grind that will also give you cache hits and misses and stuff. And those are interesting. And we do know that when we run with the new experimental JIT, for example, that the cache hits are a little bit higher, not significantly, but a little bit higher than when you don't. So those kind of tools are interesting, and I think that's where like I'm talking about like let's collect more signals that kind of would tie break the noisy timing data. And I think they fit into that category. But in terms of using something like RR, I haven't thought of that. That's a really interesting idea, and I think that would be worth exploring. Because like you say, you could just rerun the CPU parts of what happened. Yeah. Yeah. Yeah, cool. Thanks for the suggestion. I'll definitely look at it. Good question.
Thanks for the great talk. I was curious if you had any observations or tips on dealing with noise, specifically coming from like the CI and virtualization there.
So I did do some experiments running this in virtual machines on Azure and stuff, and I think it increased the noise like by an additional 2% or so. And when we're looking, when our changes are so small, it just sort of didn't help. There is a paper where they claim that they got better, and I tried to implement all of its ideas. Like one of the things they suggest is like, don't run the whole suite on A and the whole suite on B. Run it interleaved, so like run old code and new code right next to each other, so that if your performance profile on the machine is kind of going slowly up and down like this, at least your comparisons are close together. And they say that helped them a lot in the paper, but I couldn't get that to really have any impact. So like it would be really nice if we could run this on a VM for like the security reasons and cost reasons and all kinds of things, but I haven't found a useful, reliable way to do it.
Do you know where I could find that paper? Or?
I'll look it up and send it to you. I know who you are. I'll find you.
If I was to submit a PR benchmark, what information would you like to have other than a chunk of code drop?
Like a basic description of what it's doing. If it uses a big library and understanding of kind of what its dependencies are, to make sure that those are dependencies we can deal with relatively easily. but yeah, I mean, that's about it. Some way to kind of confirm that it's doing a thing that the application typically does, you know? So it's not just another. We would like to avoid adding more toy benchmarks. I think we have enough of those, so.
I forget what it's called actually. The non-geometric mean testing. HAPT?
HPT,
HPT.
hierarchical performance testing.
There seems to be a mix of, is this significant versus how much difference does it make? So I'm wondering, is there a way to separate those out? Because if we're doing a small change, obviously the interesting thing is it making it better? It almost doesn't matter how much. If it doesn't make it better, we don't include it. If it does, we do. But if you're comparing like 311 to 310, what you're really interested is how much better is it? Because it's pretty obvious it's significantly, statistically significant.
Right. Yes, so it gives you kind of two modalities, and I can show, so like, I'll just pick a benchmark at random. If you look at one of these results, it will say, you know, the HPT reliability, like, so the geometric mean on this one is 13% slower, but its HPT is 100% certain of that, and then it tells you at the 99th percentile, however, so 99% of the time, it's only 6% slower. But 100% of the time, you know, so you get that nuance. So I think for, you know, how much is it slower, you're looking at this number, and how much slower you're looking at this number. Yeah.
So will there be also free threading benchmarking suites and sub-interpreters and the like benchmarking suites? And do you expect them to be full replacements or to be some benchmarks in that suite?
Yeah, so Eric Snow has already been working on parallelism benchmarks, and I think Anthony Shaw has as well. He's talking tomorrow. I don't see them as replacing this. I think the single-threaded benchmarks will always be super useful. I see it as kind of augmenting that so that we can measure the, you know, that's going to be super useful for measuring the effectiveness of the free threading changes and such to have that suite, but it'll be, you know, in addition. We do already have some results on the single-threaded effect of free threading. Like, for example, this one says no GIL on it. So if you look at, you know, like the free threading of CPython main, right now, when you turn it on, it's about 11% slower than 312, which, by the way, all this stuff is so early. Don't run with this. Please don't go report that free threading is not helping or anything. This is all experimental code, but we are starting to measure this so that we kind of know and can track where it's going. I think there's a question there, though we are technically out of time, I guess, too, but.
This is more a note than a question, but your talk assumes that every change can have a positive, neutral, or negative effect. But what I saw in practice is that sometimes you are making some code faster and other code slower, or a bit faster but more memory pressure, which will become slower later. How do you deal with it?
Well, for our team, most of the time, we're trying to understand how it affects it across the board. So if it does make something faster but makes something else a whole lot slower, we would probably not do that thing. But there are, you know, pull requests like, you know, Carl Meyer was working last cycle on generators and making them faster, and it was really helpful to have the generator benchmark and see that one kind of move ahead. So this is why I think the one number is never going to be super helpful. Like having the ability to look at individual benchmarks is always useful. So you can make a judgment call and say like, okay, yeah, it made this edge case slower, but it's making a common case way faster. So let's do it. You know. All right, thank you very much. I really enjoyed having the discussion.